Uh, Slightly, I rushed a bit while covering the Hamming bit part, Hamming code part, because I thought we will cover it in the tutorials. Okay. So what we did, what we covered in the Hamming bit part is, we were trying to do the error detection and error correction code. We have looked very carefully about error detection. There were two methods. One was the parity method and other was the checksum method. Parity method, you know that again there are two different types. Either it may be you can check for an odd parity, that is this number of ones in the bit that is in the binary word that is being sent must be odd. Similarly, you can have an even parity error detection method also. So we have seen that in the last class. Error correcting codes also we just saw, but still I will repeat it again. Error correcting codes, as I said in the last class, there are multiple different types of Hamming codes. It can be 7-bit, 15-bit, 12-bit, 20-bit, 40-bit, 60-bit, any number of bit Hamming code is possible, and these are called as error correcting codes. What do you mean by error correcting codes? Is, say for example, if the system identifies that there is an error, it will automatically find out, it will find out that there is an error, and it will automatically correct it. How is that possible? How is that possible is moving what is a Hamming code. A 7-bit Hamming code looks like this. Okay. And how does uh, maybe you can take some random number. Okay. So 7-bit Hamming code looks like this, in the sense parity bit and data bits, they will exist combinedly. They will coexist in fact. Meaning that if you want to send an 4-bit data word, then you will append the parity bits also along with that. In case of an odd parity and even parity, what we saw was the first bit will always be a sign bit, right? The parity bit, we call them as a parity bit. If I am sending an 8-bit word using an odd parity, then it means that the first bit will be a parity bit and rest all will be data bits, D2, D3, D4, D5, D6 and D7. If it is a 8-bit parity bit. Here, in order for you to send just 4 bits of data, you are having 3 different parity bits, and each parity bit will check for a combination of data bits. For example, if I have, I'm trying to slide this down, it's not moving. Yeah, old system. Yeah. Okay. So if I'm using a 7-bit Hamming code, in 7-bit Hamming code, what are the two positions that are possible? Two positions that are possible are 2 power 0, which is 1, 2 power 2, 2 power 1, which is 2, 2 power 2, which is 4, 2 power 3, which is 8, and this is not possible, right? Why? Because I'm having only 7 bits. In 7 bits, which means that P1 will be occupied by the parity bit, and then P2 will be occupied by the parity bit, and P4 will be occupied by the parity bit. Okay. So which means what is P1 is the first bit, P2 is the second bit, and the third bit will be my data bit D3, P4, D5 will be my data bit, D6 will be my data bit, and D7 will be my data bit. If I am having, so I will take a larger number now. if I'm having, say for example, 18-bit Hamming code, just a random 18-bit Hamming code, how many 2 bits positions are possible? 2 power 0, 1, 2 power 1 is 2, 2 power 3 is 8, 2 power 4 is 8 2s are 16, 2 power 5 is 32, and this is not possible. 2 power 5 is not possible. 32nd bit position for parity is not possible, which means now P1 is my parity bit, which will occupy my first bit position. P2 will also be my parity bit. Oh, I missed 2 power 2, I missed. So 2 power 2 is 4. So P4 will be my parity bit. Okay, between P2 and P4, there is a bit position that is left that will be occupied by my data bit D3. Okay, now P4, then next bit parity bit position is 8. So till then I will occupy, the data bits will occupy their positions D5, D6 and D7. They are occupied by my data bit, and D8 here, P8 will be my parity bit, and next my parity bit position will be P16. So D7, D9 now, D10, D11, D12, D13, D14, D15, and 16th position will be occupied by my parity bit P16. And after P16, it is an 18-bit Hamming code. So I will have D17 and I will have D18. So this is how the complete Hamming code will look like. Now comes the next point. What is the next point? I've already said that each parity bit will check for a combination of bits. Meaning for a 7-bit Hamming code here, P1 will check for D3, D5, D7. P2 will check for P2 its own bit D3, D6 and D7. P3 will check for P3, D5, D6, D7. How did I get this? I cannot keep on remembering this, right? It is very simple. How did I check this is P1, I should have made a table. Never mind. I'll make a tick mark. Okay. So okay. Now P1 will check for the alternate number positions. That is, it will check for 1, it will check for 3, 5, 7, 9, 11, 13, 15, and 17. Now P2 will check for, it will start from P2 only. Okay. So P2 will check for, since its weight is 2, it will check for 2 consecutive bits and it will leave 2 consecutive bits, which means it will check 2 and 3, P2, D3, D5, D6 it will check, it will leave D7, D8, D9, D10 it will check, it will leave 11 and 12, 13 and 14 it will check, it will leave 15 and 16, it will check for 17 and 18. I hope I have made it clear. Similarly, the parity bit P4 will start from P4. Okay, it will check 4 consecutive bits and leave 4 consecutive bits, which means P4 will check for P4, D5, D6 and D7. It will leave 8, 9, 10, 11. It will check for 12, 13, 14, 15 and it will leave 16, 17, 18. Okay, now, yeah, please.
So you said P2 will check for P2, P3 and D5, D6, right? So that there is only one was left, that is P4.
Oh, yes. You are right. So let me redo this particular part. So it will check for 2 and 3, 4 and 5 will leave, 6 and 7 it will check, 8 and 9 it will leave, 10 and 11, 12, 13, 14, 15 and 17, 18. Am I right now?
Yes, sir.
Yeah, okay. Now P8. For P8, it will start from 8 bit. So it will check for 8 consecutive bits. So 8, 9, 10, 11, 12, 13, 14 and 15 it will check and it will leave 8 bits. For your sake of convenience, I did it for 42 bit. I did for 42, I think 40 bits. You see here, top row, I just made an Excel sheet for your convenience. So there are, how many bit positions are there? There are, I think 40 bit positions are here, right? Yeah, 40 bit positions are here. Okay. Now, what are the parity bit positions they will occupy? It is 2 power 0, which is 1, 2 power 1 is 2, 4, 8, then 16. After 16, it is 32. So it is 32. It has occupied these bit positions, parity bit positions. Now, now P1. P1 you can see alternatively they will check for those particular bits. It will check for P1, P3, P5, P7, P9, P11, P13, etc. Similarly, P2 will check from P2, it will check for 2 and 3, it will check for 6 and 7, it will leave 4 and 5. It will again leave 8 and 9 and it will check for 10 and 11. It will leave 12, 13 and it will check for 14, 15 likewise. Similarly, you see P4, it will check consecutive 4 bits and then it will leave 4 consecutive bits. Again, it will check 4 bits, it will leave 4 consecutive bits. Okay. Similarly, P8. P8 will check for 8 consecutive bits. It will leave 8 consecutive bits. Right? You can see the number. It is 8 cells are here. And likewise, this keeps on continuing till my total number of bits. Okay. So I hope I have made it clear. Okay. All right. Now, let me come back. Now, we said that these are error correcting codes, right? So first let us encode the bits and then we did this, we saw this problem in the last class, but still I am repeating. Okay. I need to encode 1101 into a 7-bit even parity Hamming code. So these are the data bit positions. So where is the first data bit position? D3 corresponds to this one, D5 corresponds to this, D6 corresponds to 0 and D7 corresponds to 1. I have filled out my positions now. Since I am checking for an even parity bit, so P1, you know that it will check what are the positions. It will check for 3, 5 and 7. So 3 corresponds to 1 here. So 3, 5 and 7. 3 corresponds to 1, 5 corresponds to 1 and 7 corresponds to 1. And what is the bit I have to make? I have to put for P1 so that I make this pair an even parity only. So this the number of ones in all other bit positions here are 3. It's an odd number. So if I'm checking for an even parity, P1 must be made equal to 1. Right. So I will make P1 1. Very bad color. I will make P1 1. Okay. Now P2. P2 will check for these two, leave 2, and then it will check for these two, which means it will check D3, D6 and D7. So it is 1, 0 and 1. It's already even. So P2 will be made 0. Now P4 will check for 4 bit positions. 4, 5, 6, 7. So it is 4, 5, 6, 7. 1, 0, 1 is the value and it's already even. So P4 will occupy 0. So this is the complete Hamming code which will be sent 1, 0, 1, 0, 1, 0, 1 for an even parity Hamming code. Now let us correct the error now. Okay, I'm going to correct the error. Obviously, since you are computer science students, you can create algorithms for identifying these also. Now let us take one example. The first example, please note here, read the problem. check for error and correct the message sent that is coded in 7-bit Hamming code. This is the Hamming code that is being sent. I have to find if there is an error or not. First, I have to find what are my parity bits, right? So P1 will be my parity bit. So what are the combinations? 1357, 2367 and 4567 are the parity bits. This is a 7-bit Hamming code. I have to check for even parity. Okay, this is not written here, but I will check for even parity. So 1357, what are the bit positions? It is giving us, this is 1 position, 2, 3 position, and this is 5, and this is 7th bit position. Okay, and 1001, the number of ones here is even, so this parity is okay. So which means that I have to correct also, right? Please note here, I have to correct the message also. So I will create a correction code, something like C1, which means that here there is no need of correction. So my correction bit is 0, corresponding to my first parity P1. Okay, next parity bit P2 corresponds to what? 2367, right? 2, 3, and then I will leave 4 and 5, 6 and 7. Okay, so what is the bit positions? It is 0, 0, 0, 1. Because 2 and 3 are 0, 0, 6 and 7 are 0 and 1, 0, 1. Since I am checking for an even bit parity, please note here the number of ones here is odd, which means that this parity bit has created an error, the one that I have highlighted. So there is an error here. This parity bit is not sending the correct word. So what should I do? I must change this parity bit to 0 and 1. Let me not do it. Okay, which means that the correction code C2 corresponding to a parity bit 2, there is an error and this has to be changed. I am creating a 1. Similarly, P3 parity bit, it will check for 4567. This is 4. 4567 is 1001 and this is an even number of ones are here. So the parity bit has sent the code correctly and the correction code that is required here is C3 is 0. Now let me combine all the correction codes. What is the correction code that I am having? It is C3, C2, C1. Look at the sequence. Okay, this corresponds to 0, 1, 0. What is the decimal equivalent of 0, 1, 0? The decimal equivalent of 0, 1, 0 was 2, right? So 2 to the base 10, decimal equivalent. Which means that you have to complement the second bit from the left. Okay, so what is the second bit? Obviously, second bit is nothing but the P2 position, right? The second bit from the left is from here. So this P2 position needs to be complemented. So the corrected code now will become 11010001. We have corrected this particular code. We have corrected this code. Okay. Similarly, let us take the next example. Maybe I'll do one example and then I will skip. So 01101 1357. What is the bit positions? So let me write 1, 2, 3, 4, 5, 6 and 7. What is 1357? It is 0101 0101. 2367 is 1101 1101. 4567 is 1001. I am checking for an even parity, so this looks fine. This is odd number of ones, so this doesn't look fine. And here this looks fine. I think there is a mistake. Yeah, there is a mistake here. So 1 needs to be changed to 0. So this correction code must be 1 here and this correction code must be 0 here. Again, okay, I'll take another example because I've done a mistake in this part. Yeah. So the correct answer is what is equivalent to 010? The correct equivalent to 010 was 2 and I have to change my second bit position from 0 to 1. So this will be the corrected code. Okay. Similarly for 1110 maybe I will do it. What is the value? I think the problem is the 1110 110. 1110110. Okay. I'm checking for P1. I'm checking for P1. So it is 1110, right? So 1, 2, 3, 4, 5, 6, and 7. So I will check for 1, 3, 5, 7. 1, 3, 5, and 7. So number of is odd. So which means that I have to change the parity bit that has created is wrong. So C1 will be 1. I need to change this 1 to 0. Okay, P2 parity bit is, it will check for 2, 3, 6, 7. So 1, 1, 1, 0. This also needs to be changed. So C2 is also 1. P4 will check for 0, 1, 1, 0. So the number of ones are, this is also wrong. It's right. So C3 will be 0. Now, in order to correct this, what is the bit positions? It is 0, 1, 1 corresponds to 3. So I have to change my third bit from my left. So all I need to do is, this is my error code. 0, 1, 1 is my error code. I need to change this from 1, 1. The third position bit I need to change from, I have to complement it. So this 1 becomes 0 and then 1, okay, 0, 1, 1, 0, right? So this is the corrected bit. This is the corrected having code bit. Now, always as computer science students think, can you write program for this? Can you identify the bit position, create an error code like this, and then complement the corresponding bit position, right? So you must be capable of writing a program for checking this. Any doubt? So we are done with the error correcting and error detecting codes, Hamming codes. Any doubt?
Excuse me, sir.
Yeah.
So if we had 5 corrections to make, then which bit size will we consider to convert it into decimal?
Sorry, could you repeat the question? What is that 5 corrections? I didn't get that point.
Suppose, sir, we have 5 corrections. Like in this case, we took 3 corrections. Now we have 5 corrections.
It is not corrections. This is an error code telling you that the third bit needs to be complemented. Okay. So if you have, okay, I got it what you are trying to say. If say for example, I am having 2, 4 and then after this it is 8, right? If I am getting P8, some code is there, C4 to be as 1, then which means that it is 1101, right? What is equivalent to 1101? It will be 10, 11, 12, 13, right? So 13, so the 13th bit position from the left needs to be complemented. So 13th position from here, 8, 9, 10, 11, 12, 13th bit position needs to be complemented. When you complement it, you will correct that particular error. Have I made it clear?
And sir, if it would have been 5, then
Okay.
how do we say
Okay. So which means that if the number is 5, right? If the number is 5, then if the decimal equivalent is 5 here, then this bit needs to be complemented. So this 1 will become 0 here.
No, sir, I meant if we have 5 parity bits.
Okay, 5 parity bits as in this particular Excel sheet.
P16 was
Yeah,
once
5
having.
parity bits. What is 2 power 5? 2 power 5, can you quickly tell me the answer? 2 power 5 is what is
32.
32, right? So let us assume that I am getting a code something like 10110, right? What is 10110 equivalent to? Say for example, I am getting C1, C2, C3, C4 and C5 as 10110. What is this 110 equivalent to?
22.
Sorry? 22.
22.
22, right? So I will change the 22th bit position. Which is 22th bit position? This is the 22th bit position. I will change this.
Okay, sir, got it. Thank
Got
you.
it? Yeah. Okay. I think I did some example here. I am not recalling what is the example I did. See, 1011, something to I did. Okay. Right. That's okay. So with this, we are done with the error correcting and in fact the codes in general. Now coming to the digital, the algebra, right? What is the algebra is all about? Algebra, before moving on to the algebra, let's concentrate what do you mean by a digital circuit, and then slowly let's move on. Okay. So any digital circuit, you know that they are going to handle only the binary, right? Henceforth, you will look at digital circuit just as a black box with some kind of inputs on one side and some kinds of outputs on the other side. It is something similar to this. You are having an IC. Okay, so you are having an IC. What is that you are interested in? You are not at all interested in what is the internal connection of the IC. All you are interested in is what is that I'm giving as an input and what is that I'm getting it as an output, right? That is what I'm interested in, right? So here also, henceforth, we will set our mind such that we will consider any digital circuit as a black box and then we will operate. Now let's move on to algebra. Why should we study Boolean algebra? Why? Because we are going to implement something like in algebra, what is that we do? We try to solve for a particular variable, right? So here also we try to simplify the binary logic. So that is why we use this Boolean algebra. So because binary logic is used in all of the digital computers and devices, the cost of implementing those particular circuits will be very large. So say for example, I have a polynomial. So some random mathematics polynomial. So x cube plus x squared plus x plus 25, 25 equal to 0. You will not like to solve this particular polynomial as it is, right? If this polynomial, if I ask you to find out what are the factors of this polynomial, definitely you cannot visualize. Instead, if I give you an expression something like x plus 3 multiplied by x plus 2 multiplied by x plus 20 equal to 0 and I ask you the factor, you will immediately say that the factors of this polynomial is 3, 2 and 20 or minus 3, minus 2 and minus 20. You will immediately say that these are the factors of this particular polynomial. Similarly, what is the need for an Boolean algebra here is if you are trying to implement a Boolean logic, then the number of digital circuit that you need is very large. It is always required that you simplify that particular thing and then you implement it. Why we should not implement as it is similar to this particular example, right? It is complicated in normal algebra. In case of digital algebra, that complication is nothing but, though they will look simpler here, the Boolean algebra expressions, but binary logic expression, sorry, but their implementation cost will be very large. So in order to avoid that, and the circuitry will also become complex if you don't simplify those binary logic. So hence, not, in order to find a simpler and a cheaper logic, an equivalent realization of circuits can get you a very good payoff by reducing the overall cost of a design. Say, for example, you might have seen some the toy mobiles that they sell in some functions, right? It will just create some music. You press number one, it will create a music. It will look like a phone only, right? It is just a simple toy. What is that they have? They have a simple, very, very simple logic of creating a connection, right? So which means that they have simplified using some binary logic that fits into a very, very small device. Most of the toys, most of the blinking circuits, right? Everything is created by using binary algebra and simple logic only. Okay. So what is a binary algebra? It is a mathematical model that simplifies the circuits that apply the logic of Boolean algebra. Right? So these are, let us see what is that, what is the background behind Boolean algebra. It was named after the inventor known as George Boole. Right? What did he do was, like any other mathematical system, Boolean algebra is also represented as a set of elements. Right? In case of a polynomial, we represent in the set of variables, right? So similarly here, they are represented as a set of elements, and these elements we can apply certain operations on it. Operation in the sense the arithmetic operations. You can perform addition, subtraction, multiplication and division on these elements, and then based on the operation that you perform, there are certain theorems that has been created. Theorems or postulates or axioms that has been created. Say for example, as given here, 0 plus x is x. Here it is, you must not think as a normal addition of x and 0. You must think as a logical addition here. Now here, when we say the operations, definitely we are going to add, but addition is slightly different here. Okay, so the events that they occur here, there are two kinds of events. Either it may mean, since we are dealing with binary, right? Either it will be true or false, or it will be yes or no. Either it is logic 1 or 0. Right? So this is what is the events that will take place in a binary system. And how are they connected? How are they connected are using this set of operations. Okay, either you, this, we will not call this as a plus in Boolean algebra. We will call this as an OR operation. We will not call this 0 dot x as 0 multiplied by x. We will call this as an AND operation. We will not call minus x. We will not call this as a, we will just call this as a x naught or x bar. Okay. Now, this Boolean algebra, it was, though it was initially started with George Boole, later on it was developed by someone called as Shannon. Now the Shannon's theorem is very, very powerful. He introduced this Boolean algebra using, replaced this Boolean algebra as a switching algebra, right? So as I said, there is one course on error correcting and error detection codes, right? In that, the Shannon's algebra, that is the switching algebra, is very widely used. Okay. In that particular case, you will have multiple values. In case of Boolean algebra, you know that it is 0 and 1 only, right? So in case of a switching algebra, there are different additional multiple logical positions. Okay. Now, let us start what is a Boolean algebra is. Boolean algebra, it will have set of elements 0 or 1. And the operations that you can perform are, you can perform a dot operation, right? Please note, I am not telling it as a multiplication operation. It is a dot operation, an OR operation, that is a plus operation, and a complement operation. Complement means the negative. Say, either you can represent this negative as like this, a bar you can write, or in certain books they will write it as a complement like this, a dash. These are two different ways by which you can represent a negative number. Again, though preliminary, it is important that we will start from the basics. An AND gate, if AND gate, how do I draw an AND gate? This is how I draw an AND gate, a straight line and a arc. This AND gate will have two inputs and then it will have one output. This is called as a two input AND gate. Okay, and how does this perform is, this will give you an AND operation. AND operation, what do you mean by that is, when I say A and B, since this is this Boolean thing is a two valued operation here, the variables, the inputs A or B will assume two values. So which means either A will assume 0, B will assume 0, or A will assume 0, B will assume 1, A will be 1 or 0, or A will be 1 and B will be 1. Meaning, when this is 0 and 0, the output of my AND gate will be 0. A dot 0, 0 into 0. I am purposefully saying multiplied by. 0 dot 1 is also 0, right? Is also 0. 1.0 is also 0 because 1 multiplied by 0 is 0. 1 multiplied by 1 is 1. I purposefully said multiplication. But when you read, you must say what is that you need to understand here is, unlike a normal multiplication, you should not look this particular part as a normal multiplication, right? What is that you need to observe here is, you need to observe as a combined input how your AND gate is responding. If you see here, whenever any of the input is 0, right, your output is also 0 here. Your output is 1 only when both the inputs are 1. This is what you need to analyze for an AND gate, not a direct simple multiplication. Similarly, this AND gate, what you see here is a circuit symbol. What you see here is a circuit symbol. Now, I should not have written like this, circuit symbol. Now, what is that you will have inside this AND gate? Inside this, either you will have a combination of diodes like this, or you can have a combination of transistors like this. These elements are called as diodes. These elements are called as diodes. What is these diodes? They are semiconductor devices that perform this switching operation. These elements are called as transistors. Again, transistor is an extended version of these diodes. They also perform the switching operation, but these transistors will have more control over the output than compared to the diodes. Okay, so this using a diode and implementing an AND gate is called as a diode logic. Using transistors and resistors here, this is called as an RTL logic. I should have called only RTL, but by convention it has become as an RTL logic. Double logic ho gaya. So R represents for resistor, T represents for transistor. So resistor transistor logic. There are also some logic called as TTL logic. What is TTL logic? Transistor logic. There you will not have these resistors. You will have these transistors replacing these resistors. Okay, let us not go into semiconductor devices now. Let's focus more towards the digital electronics. Now, similarly, OR gate. The circuit symbol of an OR gate is like this. You will have a curved R and then you will have this. You notice in the previous case, I have written some number as 7408. What is that is, this is nothing but the IC number in which you will have AND gate. And IC, if you go to the market and ask for a 7408 AND gate IC, you will have AND gate inside this. I mean, you might recall your lab exercise, right? So you will have multiple AND gates inside this. Okay. Right. So some combination of gates like this, right? So this gate, the AND gate IC is called as 7408. That is why I have written here as 7408. Similarly, if you want an OR gate, then you have to ask for 7432 gate. Though this number, it looks difficult for you initially to look at, but over the period of time, as you keep on using these numbers again and again, you will remember immediately the IC numbers. Okay. Again, here also the observation is very important. It is 0, 0. The output is 0. I made a mistake here. 0, 0. The output is 0. 0, 1. The output will be 1. 0, 1, 0. The output is 1. And 1, 1. The output is 1. What is that again you need to observe here is, you need to observe when are you getting 1. You are getting 1 when at least one of the inputs are 1, right? Here at least one of the input is 1, you are getting 1. And similarly, so this is what is that we call these tables as a truth tables, right? So 1 plus 1, do not confuse the last part. Now it is 1 plus 1 is not 2. Or in binary addition, it is not 1 plus 1 is 1, 0. No, right? Don't confuse this with the normal decimal addition or with the binary addition. This is a logical OR addition, logical OR value. When both the inputs are 1 and 1, you will get 1. Even if any of the input is 1, you will get 1. If both the inputs are 0, your output is 0 across an OR gate. And this is the diode logic for a OR gate, and this is the RTL logic, resistor transistor logic for a transistor for an OR gate. Please look at the configuration. Though I skipped a bit, you must always remember these things. You see here A and B here, they are connected in series here. They are connected in series, and then some output is taken here. Okay. So here, this transistor and this transistor, they are connected in parallel. They are connected in parallel, right? So these small things you must remember. Right? So here they are connected in series, and here in case of a diode logic, this D1 and D2, they are connected in the reverse bias. I hope you have studied what is biasing in class 11 and 12. Whereas in case of an OR logic, these diode D1 and D2, they are connected in forward biased. Okay, at least these things you will remember. Now coming to NOT gate. What is the circuit symbol of a NOT gate is? So this is the circuit symbol of a NOT gate, right? You will create a 0 here. This bubble represents that, the complemented form. Complemented form. What do you mean by complemented form? You give 0, your output is 1. You give 1, your output will be 0. Okay. And this is the transistor RTL logic. RTL logic. Okay. All right. Any doubt till this? Okay. Now, these are called as these NOT gate. The other name of a NOT gate is called as an inverter gate. This is also called as an inverter gate. Okay. And where it is applied is the application of inverter is whenever you want to perform one's complement, right? You want to perform an one's complement, right? How do you perform one's complement? If 0, 1, 1 is the actual number and you want to take one's complement of this, you complement every bit, right? 0 bits converted to 1, 0 and 0. So there in these circumstances, wherever you want to perform one's complement, then you can apply these inverter configurations. See, 1 becomes 0, 0 becomes 1, 1 becomes 0, 1 becomes 0 and 0 becomes 1. In addition to these three circuits, that is AND, OR and NOT, right? There are more gates, a combination of these gates in fact, called as universal gates. What is the combination of this? That is, if you combine AND gate and NOT gate, so this is your AND gate, this is your NOT gate, AND and NOT gate combined, this is called as a NAND gate. Similarly, you combine OR gate and NOT gate here, OR gate and NOT gate here, you get a NOR gate. And the combined circuit symbol of this, as I said, NOT gate means it is just nothing but a complement, right? The bubble here represents a complement. So this is an AND gate. This is an AND gate here, two inputs, A and B. So what is the output here? The output will be A dot B, right? I create a NOT, what will become the complement of this? Complement, how do I write? If I am having A as an input, I will write A bar as a complement. So A dot B is the output and I am crossing it through a NOT gate, it will be a whole complement. So this can be simply drawn as A and B is an input. I just put a bubble here. And then my output here will be A dot B, the whole bar. This gate is called as the NAND gate. Similarly, you perform the operation for a OR gate here. This is called as a NOR gate. Okay, so these two gates, NAND and NOR, they are called as universal gates. They are called as universal gates. Why they are called as universal gates? Because any combination of these circuits, AND circuit, OR circuit or NOT circuit, can be implemented using either NAND or NOR. Next, let us look at a bubbled NAND gate. I think it's 250. We'll wind up here. Maybe we will continue the gate. Now it'll get really interesting. Playing around with gates, it will really get interesting. So we will continue this gate part from the next class, that is on Wednesday. So if there is any doubt, you stay on.